You may not realize it, but we've already looked at the limits of piecewise functions. However, we've only looked at the limits of piecewise functions based on their graph. So any of those graphs that we've looked at in class where you had one side approaching something and another side approaching something else, the reason they're approaching different things is because they have two different functions for each piece, a piecewise function. So now we're going to look at what if you're actually given the function and not the graph. So in order for a limit to exist, don't forget the left and the right side have to be the same. And if you think back to the work that you've done with piecewise functions, sometimes piecewise functions are going to be continuous, meaning the left and right side will approach the same thing. Other times it will not. So let's go ahead and look at, I think I have one example on piecewise functions. This is kind of one big example. And then we're also going to talk about types of discontinuity, which is a review from a previous course. So the limit as x approaches 1 from the left. Remember, if I'm approaching from the left, I'm coming from the values that are smaller than 1. So if I'm looking here at my piecewise function, notice that that is talking about this piece right here. So if I'm coming in from the left, all I have to do is look at the top piece of this function. Well, the top piece of this function is going to allow me to use direct substitution, so the limit as x approaches 1 from the left is going to be equal to 1 squared plus 3, which is just 4. Looking at the second part, now I'm finding the limit as x approaches 1 from the right. Well, again, if I'm approaching from the right, I'm only talking about numbers that are bigger than 1. So again, I only choose one piece of the piecewise function. This time, since I'm coming from numbers bigger than 1, I'm going to choose the piece that has numbers bigger than 1. Again, I can use direct substitution. Since there's nothing to plug in for, and since I understand that a constant means it's just that horizontal linear equation and every single value is going to be equal to 7, I know my limit as I approach 1 from the right is also going to be equal to 7. So then my overall limit as x approaches 1, not from the left and not from the right, does not exist since my left and right are different. If my left and right had been the same, then my overall limit would exist. So for piecewise functions, just choose which piece you're working with and then try to use direct substitution. If you can't use direct substitution, use some of the methods that we've already learned, or as we move through this unit, some of the methods we're still going to learn. From here, I also want to talk about types of discontinuity. We've covered this before. Remember that there's two different types of discontinuity. We can have removable points of discontinuity, and we can have non-removable. Removable points of discontinuity are always going to cause a hole, whereas non-removable will always cause a vertical asymptote. So if I look at these examples here, I'm just trying to determine where my function's not continuous and talk about if it's a removable or a non-removable point of discontinuity. In the first example, I see on the bottom there's a common factor of 3x that I could take out, and doing that's going to help me to factor. The reason I want to factor is because if I'm trying to figure out where I can cancel, where my removable points of discontinuity are, I can only cancel with multiplication, therefore I need that factoring. So again, factoring the bottom of this, top is already factored. Gives me this. I now see that I also have a squared minus b squared here, so I can factor again. And I get x plus 1, x minus 1. So now I know I have 3 points of discontinuity. I have a point of discontinuity at x equals 0, at x equals negative 1, and at x equals 1. Well, since the x equals 0 will cross out, I can go ahead and say that I have a point of removable discontinuity. I'm going to abbreviate because I don't have room here, but I have a point of removable discontinuity at x equals 0, and since the x minus 1s will cancel, the x equals 1 point of discontinuity is also removable, which means there's a hole at both of those places on the graph. And then the x equals negative 1 is a point of non-removable discontinuity. And again, I'm abbreviating more than I should just because of room purposes. And so again, I'll have a vertical asymptote there. On the second example, I see I can factor on the top. I'm going to do that again because notice how nice factoring was to help me figure out my points of discontinuity and which were removable and which were not. of x plus 8 times x minus 4 using a factor sum table. So notice my only point of discontinuity, the only thing that makes my denominator 0 is x equals 4. Since that is going to cancel out, I would say a removable point at x equals 4, and so there's a hole there, depending on what the question asks you. Just a couple more. 1 over x, notice that can't be factored, therefore it cannot be reduced, so x equals 0 will be a non-removable point of discontinuity. So there is a vertical asymptote there. F of x equals cosine of x. If you think about the cosine of x function, it's going to be that wave function. Since I never pick my pencil up, I don't have any holes, I don't have any vertical asymptotes. When I'm asked to determine where this is not continuous, this is a continuous function. I'm going to go ahead and say always continuous. We're going to, in the next video, that is not going to be enough to prove it. You're actually going to have to go through some conditions, but for right now, I'm just going to say I know the look of it and I know it's continuous. Finally, the last example, tangent of x. Well, I know that tangent of x is the same thing as sine of x over cosine of x, and therefore this is going to be undefined. It's going to have a non-removable point of discontinuity anytime cosine of x is 0. So cosine is 0 at pi over 2, at 3 pi over 2, at 5 pi over 2. In fact, it's going to be 0 at pi over 2 plus any rotation of pi past pi over 2 or behind pi over 2. So I'm going to say pi over 2 plus pi n, very similar to what we did last year when we were solving trigonometric equations. That's it for points of discontinuity. Like I said, this should be a review for you. Hopefully this looks familiar, something you've seen before. Big thing to remember is if you can remove the point that's causing the denominator to be 0, it is removable and a hole. If you cannot, it's non-removable and a vertical asymptote. Sure, any questions you have, you bring into class with you so we can address those.